In this video, let's talk about some applications of max and min that we started talking about last time. And we'll also make use of that critical number theorem that we talked about last time, that if we have one critical number, that if we test it and it happens to be a relative max or min, it also happens to be absolute max or min. So let's take a look at the first problem. Is a revenue problem. So if the price charged for a candy bar is P of X cents, then X thousand bars will be sold in a certain city. So let's pay attention to the units here because it'll be important. So here's the price, sort of like a demand equation is given, 160 minus X over 10. Then we want to find the expression for the total revenue for X thousand candy bars. So if you recall, revenue is price times X, the number of items, which we can substitute the equation, 160 minus X over 10 times X, but it's also we add 1,000 because we're talking about 1,000. It's also going to be the same thing in your homework, so pay attention to that. We're actually, the reason for doing this is that it's going to save you the conversion later, so that way we can actually avoid decimals. You'll see why we need this. So we actually multiplied by X, but also by 1,000. So we will get 160,000 X minus, if you divide 1,000 by 10, you'll get 100 X squared. So yes, we multiply by X, then by 1,000. And then we want to find the value of X that leads to maximum revenue. So as usual, let's take the derivative, which is 160,000 minus 200X, and let's set it equal to 0. Because it will always be defined, so we only need to worry about it equal to 0. Okay, so we can solve for X, move 200X on the other side, so we'll get X equals 800. This is why it was useful to multiply it by 1,000. Otherwise, we would have gotten 0.8 thousand, and you would have to think about what X means and so on. So here it's clearly we need to sell 800 candy bars. And we can test it. I like to test it using the first derivative. Sometimes on the homework examples, you'll see the second derivative, which you could also do. You could take second derivative and easily test it too. So what I did is I plotted some easier numbers, 700 and 900 on either side of 800, and I plotted it back into R prime of X. So 700 will give us 160,000 minus 140,000, I believe, if we multiply by 700, which will be positive. On the other hand, with 900, we'll get 160,000 minus 180,000. So that will give us negative. So notice, switching from positive to negative, that's like switching from increasing to decreasing, would definitely have a max. So this was the only critical number, so we assume it's a max. It's going to be also absolute maximum, if you recall the critical point theorem. So from now on, we'll just denote it max or min. That's what we're going to be testing for. Part C, now let's actually find the maximum revenue. So once we find the X that gives us a maximum, we can plug it back into the equation, which notice how I've done this, and also calculate it. So I'm getting 64 million, which sounds like a lot, but recall it was in cents. So if we divide it by 100, we'll get $640,000. And that's it. Now next couple of examples will have to do with area. If you recall this from college algebra, you may have to deal with quadratics with similar problems, setting it up, but then you had to find the vertex as a max or min. In this case, we just use calculus, so we're going to be a little bit more, I guess, high-tech or high algebra, or no, not really algebra, high math sort of situation. But anyway, let's say if we have an area situation, a campground owner has 1,400 meters of fencing. He wants to enclose a rectangular field bordering a river with no fencing needed along a river. Let X represent the width of the field. So notice I drew a little picture here. So we have X on either side with a width, and we have Y as one of the lengths. And so what we're going to do is sometimes we need to construct an equation before we can take the derivative. So this is what we're doing. 1,400 actually represents the perimeter of that fence because you're going around the outside. So if you recall, we had two widths, which was 2x plus one length, which is the y, equals to 1,400. And we can solve for y, which we just basically move 2x on the other side. I like to put variable first. So it would be negative 2x plus 1400. Now if you recall that area is length times width, so we can multiply the expression for the y, negative 2x plus 1400 times the x. So we'll get this quadratic here, negative 2x squared plus 1400x. So here in college algebra, you would have found the vertex, but you have to remember negative b over 2a and so on. Instead, we're going to use calculus. So we'll take the derivative of the equation. So we'll get negative 4x plus 1400. And let's set it equal to 0. So we'll get negative 4x equals to negative 1400. Okay. Which will get x equals to 350. And note how I'm actually testing it here. So I plugged in 300 and 400 into the a prime again. So I got, again, we're switching from positive to negative. So we have a maximum at that point. And another question was find the maximum area. So we can plug this back into the area equation. We'll get 245,000 meters squared. Okay. Now let's get back to actual business situation where we have not only area and perimeter, but we have cost with fixed area, which could be a reasonable business situation also. So here we have a fence that must be built to enclose a rectangular area of 20,000 square feet. So notice like it's an opposite situation of last time. Here we actually know the area. Fencing material costs $2.50 per foot for the two sides facing north and south, and $3.50 per foot for the other two sides. Find the cost of the least expensive fence. So just note, you can actually use different variables. You can use L and W, but keep in mind then you'll have to take the derivative using L and W. I just decided to use X for the length and Y for the width, just because it would be, doesn't matter which way you set this up. You could have switched them, but this is how I set it up. So we have area, which is known, x times y equals to 20,000. So typically in these situations, when you have two unknowns, solve for one of them in terms of the other, and then use it to construct your equation, which is what we have here. So y equals to 20,000 divided by x. Okay. Now we can construct cost equation using sort of the perimeter idea. If you recall that it was $2.50 for the north and south, which was the two lengths, so it was 2x, plus $3.50 for the two widths, which is 2y. So I got 5x plus 6.4y. And so I substituted, since I solved for y, 20,000 divided by x multiplied by 6.4. So I got 128,000 over x. Which, since we're going to be taking derivative, I just rewrote it as 5x plus 128,000 x to the negative 1 power. And we can take the derivative. So I got 5 minus 128,000 x to the negative 2nd power, which it's a little bit easier to solve if we put x squared in denominator. Let's set it equal to 0. And notice you can multiply both sides by x squared. So I got 5x squared equals 128,000, which divide by 5, we'll get x squared equals to 25,600. And then I took the square root, so I got 160. I didn't bother with a negative square root because obviously we cannot have negative length. And so now note, we always must check. So do not assume that x you get is the maximum or the minimum. So I always try to check it either using first derivative or second derivative test. So with the first derivative again, let's pick something easy like 100 and 200, some nice round numbers. Plug it back in. So I actually probably use the calculator. 5 minus 128,000 over 100 squared. I think I'm getting a negative there. Versus 200, you actually get a positive because 200 squared would be bigger than 128,000. So you'll get smaller than 5. So here you actually have a minimum situation, which if you remember the least expensive fence, you will get a minimum here. So if you read the question ahead of time, okay? So it's 160, but we need to find the actual cost. So I plugged it back into C of x. It was 5 times 160 minus 128,000 divided by 160. So I got 1,600 here as the answer, okay? And now we'll take a look at one more example that has to do with a volume that's actually used in the postal service. So here it stipulates that any boxes sent through the mail must have a length plus girth, which we will define, totaling to no more than 108 inches. Find the dimensions with maximum volume that can be sent through US mail, assuming that the width and height of the box are equal. So we're trying to find maximum volume, which, if you recall, it's length times width times height. Girth is defined as like the perimeter around the face of the one of the faces, the front face actually. So it's the perimeter, and since, if you recall, that the width and the height are equal, we'll just call them x. So if you're going to go around the whole face, you're going to have 4x as your perimeter. And that's where we're going to use that condition, length plus girth. No more than, we're actually going to set it to equal to exactly 108 because we were trying to find the maximum. So instead of using the inequality, we're going to set it equal to. Okay, so here I have, this is actually L. I used L for the length, so it would be the length plus the girth, which is 4x, equals to 108. Okay, which we can solve for L here. Just move the 4x to the other side, so you'll have 108 minus 4x. And then I used this for the volume equation, which is length times width times height. So length was 108 minus 4x times the width was x and the height was x. So that's x squared, and then you distribute it, so we'll get 108x squared minus 4x cubed. So you should have an x cubed for the volume. So we can find the maximum, take the derivative. So I got 216x minus 12x squared. Set it equal to 0. And what do we have? You could pull out an x. So you'll get x times 216 minus 12x equals to 0. So you'll have x equals 0 or x equals 18. So x equal to 0 doesn't make sense. You're not going to have a box, so we're going to throw that out. So we only have 18, which we can test. I tested with 10 and 20 to plug in into v prime. 10 will give us positive, I believe, because it's going to be positive times positive. And 20 will give us positive times negative, so the product would be negative. So notice 18 does give us a maximum. So the width was 18, height was 18, the length we can solve for. So I get 36. So the dimensions, which was asked, the dimensions of the maximum volume are 36 inches by 18 inches by 18 inches. And that's it for this section.